Ask a language model beats music is owned by, and it answers Apple. We've known for a while that facts like this are stored in the model's weights, and thanks to work like the Rome paper, we even know roughly where, in the mid-layer feed-forward modules. But knowing where a book sits on a shelf doesn't tell you how someone walks over, finds it and opens to the right page. That retrieval process, the actual mechanics of getting a fact out during inference, was still a mystery. This paper from Google DeepMind and Tel Aviv University set out to trace it, and what they found is a surprisingly clean 3-step assembly line. It's worth being precise about the gap they're filling because it's a subtle but important distinction. Previous work asked a localization question: if I corrupt or restore this piece of the network, does the fact survive? That tells you where knowledge is stored. This paper asks a different question. During a single forward pass, how does information actually move from the words of the question through the network to the final answer? That's a question about flow, not location. And to answer it, you need a tool that can interrupt the movement of information rather than the storage of it. The experimental setup is deliberately simple, which is what makes the results so clear. Every query has the same shape, a subject and a relation, asking for an attribute. Beats music is the subject, is owned by is the relation, and Apple is the attribute, the answer we want. Now the model reads these tokens left to right, building up a representation at each position. The final position, the one right before the answer, is where the prediction gets made. So the question becomes concrete. How does information about beats music and information about the ownership relation both find their way to that final position and combine into Apple? Their instrument is called attention knockout, and the logic is beautifully direct. In a transformer, attention is the only mechanism that moves information between token positions. Everything else operates within a position. So if you want to know whether information flows from the subject to the final position, you simply block that attention edge, forbid the last position from attending to the subject tokens in a window of layers, and then measure how much the probability of the correct answer falls. A big drop means you just severed a critical pathway. Do this systematically across every layer and for each group of positions, and you get a map of when information moves. And that map reveals something striking, not one, but two distinct critical points, and they happen in a specific order. Look at the curves. When they block attention to the relation positions, shown by the dashed line, the damage peaks early, in the model's first several layers. But when they block attention to the subject positions, the solid line, the damage is deeper, and it peaks much later, in the middle to upper layers. Two separate transfers, cleanly separated in time. The relation arrives first, the subject information arrives second. That temporal ordering is the thread they pull to unravel the whole mechanism. So what's happening at the subject position during all those early layers, before its information gets transferred? This is the first step of the mechanism, and it's the most surprising. At the last token of the subject, the model builds up a representation that encodes many different attributes of that subject at once. Not just the one you asked about, but a whole bundle. Ask about beats music and that position is quietly accumulating who owns it, what kind of company it is, where it's from, and more. Think of it as the model pulling the subject's entire dossier off the shelf before it knows which page you want. Where does all that enrichment come from? A transformer position gets its content from three sources: the token embedding itself, the attention sublayers, and the feed-forward MLP sublayers. The researchers measure which one is responsible, and the answer is unambiguous. It's the early MLP sublayers doing the heavy lifting. As you move up through the early layers, the rate at which subject attributes appear in that representation climbs steadily, driven by the MLPs. This connects beautifully to the earlier Rome findings. The mid-layer MLPs really are the knowledge store, and here we can watch them writing that knowledge into the subject's representation. A natural skeptical question. Maybe attributes are floating around everywhere in the network, and there's nothing special about the subject. So they check the attribute rate at different positions, and the enrichment is sharply concentrated at the last subject token. Other positions, the relation words, the final position early on, don't show anything like the same accumulation. That specificity matters. It means the model has a definite place where it assembles what it knows about the thing being asked about. The subject's last token is the workspace where the dossier gets built. Now for the second step, which is happening in parallel and explains that early critical point we saw. While the subject position is busy enriching itself, the relation, the phrase is owned by, is propagating forward to the final position. This is what the early attention transfer was doing. And its role is essentially to pose the question. The final position now knows what kind of thing it's looking for, an owner, a company, without yet knowing which subject's owner. It's the query being assembled before the lookup is performed. Two processes running side by side, each preparing a different half of the retrieval. Which brings us to the third and final step, the moment of retrieval itself. Now the final position, holding the relation, reaches back and attends to the enriched subject representation. It effectively queries that bundle of attributes and pulls out precisely the one the relation called for, the owner, Apple. That's the second critical point in the knockout curves, the deep one in the upper middle layers. And here comes the genuinely surprising part. You might expect this extraction to be performed by the MLPs, since that's where knowledge is supposedly stored. It isn't. It's carried out by the attention heads. The evidence is direct. They measure the attribute extraction rate. How often each sublayer's update to the final position actually promotes the correct answer, and split it between attention and MLP. The upper attention sublayers dominate, with an extraction rate well over double that of the MLPs. In other words, the MLPs write the knowledge into the subject representation early on, and then attention reads it out later. Storage and retrieval are handled by different machinery. That's a clean division of labor, and it wasn't obvious before this paper. And the researchers push one step further, into the most provocative finding. They look inside those extracting attention heads at their actual weight matrices and find that these heads often encode subject-to-attribute mappings directly in their parameters. So the attention head isn't merely a pipe that moves information around. It carries a piece of the knowledge itself, a learned association baked into its weights. That complicates the tidy textbook story, where MLPs are memory and attention is routing. Here, attention is doing both, and the boundary between storing a fact and fetching it turns out to be blurrier than we assumed. To confirm the story rather than just observe it, they run patching experiments, swapping representations between different runs of the model and watching what happens to the extraction. If the enriched subject representation is really what gets queried, then transplanting it should transplant the answer, and it does. Patching the subject representation from one query into another causes the extraction to follow the patched subject. That's the causal confirmation that the enriched representation is genuinely the object being read, not just a correlated bystander. The three-step account holds up under intervention. Let me put the whole mechanism together in one place, because it's elegant. Step 1. As the model reads the subject, the early MLP sublayers enrich the last subject token into a bundle, carrying many of that subject's attributes. Step 2. In parallel, the relation propagates forward to the final position, establishing what's being asked. Step 3. The final position attends back to that enriched subject and extracts the specific attribute the relation requested. And this extraction is performed by upper attention heads that themselves carry subject attribute knowledge. Read the subject, form the question, query the bundle. That's factual recall in a transformer. So why does this matter beyond the satisfaction of understanding? Mostly because it changes how we should think about editing and correcting model knowledge. If recall is a three-stage pipeline, then a fact can be modified at more than one place, in the MLP dossier, or in the attention head that reads it. That helps explain a puzzle in the model editing literature, why some edits stick on the exact prompt, but leak the old answer when the question is rephrased. You may have changed the store without changing the extractor, or the reverse. More broadly, this paper moves us from a map of where knowledge lives to a mechanism for how it's used, and mechanisms are what let us predict, debug, and reliably fix these systems. Thanks for watching.